afternoon, everyone. My name is Wale Akinfaderi. You can call me Wale. I'm currently a data scientist with AWS, and I'm actually going to talk about this mouthful topic, which is about machine learning. When I was actually invited to come give a talk as a machine learning scientist to developers, I thought about what would be the most interesting topic to speak about. And I know in this world where we all hear things about machine learning, AI, data science, and one thing we might be sort of concerned about is fairness, which is, are we actually building the right technology that the outcomes are actually fair? And is it actually, have we actually gotten rid of the bias before building the model? So that's what I'll be talking about. Is there anyone that sort of has an interest in machine learning or does machine? Oh, okay. Good, I have my people in the room. Just a brief about me. I'm currently a scientist, like I mentioned, at AWS. Working on machine learning for healthcare and life sciences. So I actually solve problems in sort of the healthcare area. I've had some experiences developing and productionizing machine learning models in the retail space and also for renewable energy. I am actually really interested in democratizing machine learning, sort of responsible use of AI and ML, and also how you can build machine learning that is privacy preserving. So I've been on committees for machine learning conferences and also review for some publishers. In my spare time, I actually like soccer. I watch soccer. I used to play soccer. And I've also sort of played semi-professional Scrabble before, so exciting. And the agenda for today is I'm going to talk about understanding bias in data and machine learning. Fairness, accountability, and transparency. And then I'm actually going to go from that to talking about explainable machine learning. So how do you build or develop a machine learning model that you can actually explain the outcomes to people? And then I'll talk about AWS tool for finding bias in your data and your model, and also for explainability. So it's called Amazon SageMaker Clarify. And then after that, I'll talk about the MLOps pipeline. So MLOps is like DevOps for machine learning. So how do you use this tool to actually develop your pipeline? So the first thing is, what is bias? And the way I think of it is that you can have groups that are favored and actually groups that are unfavored. And so when you have prejudice against a person or a group, that is actually when you talk about bias, which is this a group that you favor, or is it a group that you don't favor? And sometimes you could actually also find them in your data set. And the next is data bias. So in most cases, when you're building machine learning application, your real world data is not the same as data that you're using for your model. Because one, you run through a lot of problems trying to get the data. So you have the data, you collect it, you don't know if you're collecting enough, you don't know if you have some errors when you're imputing the data. And so in most cases, and also you take your data and you clean that data before you build your machine learning model. And so the process from like a real world data to the data and features that you've collected, you can actually have data bias in them. And so what happens with machine learning is it's a definition or what we call garbage in, garbage out, right? So if you collect your data using unfair processes, right, and then this data is biased, what happens is that when you sort of build your machine learning model with this data, you have outcomes, but the unfair outcomes are actually amplified in this case. And so that's what happens with machine learning. It's like you give it the sort of data that is biased or selected through unfair processes, machine learning actually amplified the outcomes that you get. One really good example is sort of this problem of imbalance in your data set. So let's say you're building or developing a machine learning models on two sets of data set. One is you have the samples that are orange, and you have blue samples, right? And the distribution or the differences in the data are actually really high. So for this case, I would say the orange sample, I'll call them the majority class because you have more of it. And then the blue samples, I'll call them the minority class. And what happens is that you develop your machine learning algorithm, applies it to the data. You think you have an accurate machine learning model, but when you do inference, your predictions are actually going to be skewed to the majority. And so what happens is that the blue samples doesn't really matter in this case. And so that's how you actually see bias in machine learning, where it does actually amplify those outcomes that are unfair. So why do we even care about bias? Like why does anyone want to understand bias? And I would like to think about it from the customer point of view. So if you have customers, if you're working in sort of different fields, so I'll start from credit decisions, right? And we've seen a lot of companies, sort of banks and financial institutions actually use machine learning to make credit decisions, right? And so if you have bias in your data, in your model, in your process, it can actually affect the kind of decisions that you make when you're trying to maybe approve someone for a credit or not. You could also have it. Okay. You could also have it in marketing of products, and so sometimes maybe because of the sort of inherent bias in your data set, you build this model and you're marketing to probably the wrong set of people, for example, and you could see that. In educational opportunities, you could actually, bias can affect your customers. So for example, let's say you're building a model to make a decision on how to probably give admissions or to students, right? And you have maybe groups from maybe non-English speaking countries, right? And you're trying to use their essays, for example, to make decisions, right? And the sort of quality of the grammar structure that someone in an English-speaking country like the UK, United States, or Canada will be different from probably other non-English-speaking countries. But one thing you would notice is that is probably not the sort of accurate decider of intelligence. So there are other things that you can look at. So if your data set is biased, it can actually affect educational opportunities that they get. I've actually seen it in government services. There was a story a few years ago about a state where the court system actually using historical data to make decisions on who will be part of the members of the jury. And so the data is actually intrinsically biased, and when you build models on that, it actually amplifies that bias. And also finally in healthcare, which is really, really delicate, right? You make decisions to sort of determine if someone has a disease or not. You need to make sure that there is no bias in whatever you're building, because you're making life-changing decisions for people. And then the next thing is sort of this bias in ML. And I'm going to talk about the different types of bias that we have. The first one is the systemic errors in data. And so what happens is that sometimes maybe your data doesn't have intrinsic bias in them, but the process and the instruments that you used can actually introduce these systemic errors. Now you would see that I'm actually using errors and biases simultaneously, but they're different. So what happens is that errors is you get error when you have a single measurement. Why bias is actually a statistical property of that error. So which means you're having errors after doing repeated measures. And so, and you could see that. So let's say you have this data set of people, you can call them students, of their age, their gender, their parental education, and the final grade. Maybe you're trying to take the data and impute it into some database, some structured or unstructured format. During that process, you can actually have systemic errors. You can actually impute the wrong data set. And so that's when you start seeing systemic errors in data. This can also lead to missing data. So you could have sort of this missing data phenomenon where you just found out that maybe one column or one row is just missing. It could actually be from systemic errors when setting up your data pipeline. And so that's sort of one type of bias that you can encounter. And then, so this is it. So for example, you are imputing the grades, right? And for some of the students, you actually impute an incorrect final grade. And that would actually affect the outcome. Now, sometimes, not all features can be measured. So, so you have your machine learning system. One sort of error, or one source of bias could be feature selection. And so, for example, let's say you have incorrect final grade, but also there are some students in the class that they probably have some health conditions, but you cannot have it in the data because they're actually protected. Their PHI data, there's HIPAA compliance, so you can't use them. And so that could also be a source of bias, right? And what it means is that there might be students that maybe their grades are not going to be as good as the others because they have some health conditions and they're not around for maybe half of the semester, for example. So you would see something like that where you don't have features and you cannot actually measure that features. The next one is sampling bias. And what happens is that you cannot get all the data that you want in this life, right? So data is, the velocity is high, the volume is high, and most times a lot of data keeps streaming in, right? So, and what statisticians or data scientists, what they do is that they actually sort of sample the data that they want, they develop a sampling technique, and they get a percentage of the data that they want to use. But at some point, your sampling bias, you have to account for some errors, some statistical errors in that process. So they are unable to collect all data over all time. And so, for example, let's say you have sort of this data that I'm actually using as an example, but the math students, you don't have their mathematics grade, for example, and there's no way to correct. So that can actually, so that's actually a bias that you can have in your data set. And finally, I think as human, we have some inherent bias in us also, so which is, this last one is human bias. And sometimes it's like when you're trying to build a model or develop a data set, there's some intrinsic bias. There's some set of people, some group of people that you would actually just gravitate towards and say, oh, this is what I want. And so example for this actually data set for human bias is when you actually favor alumni. So you said, oh, okay, because I mean, this person is from my school, my high school, my middle school. I think, yeah, I'm actually going to favor them. So you can also have sort of this human bias that would affect the outcome of your machine learning model. And so what happens is that if we sort of combine everything, the sort of human bias, the sampling bias, the fact that you cannot measure all the data over time, and you take everything and you actually apply machine learning to it, what you have is actually you have unfair outcomes. And that's what happens. And next is, what can you do so when you have bias, how do you even combat it? So the first thing you want to do is understand the data distribution. So if you have a data set, as a machine learning practitioner, or as a data scientist, data analyst, as long as you work with data, sort of understanding the data distribution, and also sort of doing exploratory data analysis, understand your data, explore your data is extremely important. With that, you sort of understand the distributions in the data, and with that, you can find some sort of bias that is embedded in your data set. And then you also want to sort of understand the data distribution over time. So so for example, maybe this semester you have five students with health conditions. Next semester you have 4. The other semester it changes. So you actually want to know the variability, how your data actually changes over time. It's very important. And so next is, I want to talk about these 3 key points. which is fairness, accountability, and transparency in machine learning. And so for you to be able to build fairness in machine learning, there are 4 things that you need to consider. You need to understand the bias in your data set, the bias in your models. You need to monitor the changes. So when you deploy a machine learning model, you want to monitor the changes over time. And then you can actually adjust your model for fairness in this case. And then the next one is, how do you actually address bias and fairness? Improving sort of the quality of your data set is very important. What I've seen people do is they have like quality control, data quality control team, where these are like quality engineers that they can actually check for data set if there is sort of an underrepresented group in that data. They try to get more data for it. They also try to improve the feature selection, and then they also, monitoring the changes in your data over time actually helps. And then there's this sort of idea of rebalanced data, which what you do is that you have sort of a group or a data set that is underrepresented, and then you do data augmentation. In machine learning terms, we actually call it sort of oversampling the minority class in your data set. So you can actually do that, or what you do is you can actually filter down the sort of overrepresented. So I can give you an example of where people use this a lot. So every company, they sort of have like a fraud and risk unit where they actually build machine learning to detect fraud in real time. But the problem is that if they have 2,000 set of examples, historical examples, maybe just 5 of them will be related to fraud, right? And the remaining 1,995 are seamless transactions. And so in that case, they have a lot of data that is overrepresented. So they use some of these techniques to rebalance the data when they build their models. And then the next one is in machine learning, you can actually include some constraints, some fairness constraints. And also you can select your model based on fairness criteria. So, and also you can monitor the changes in your models. You can monitor them real time. And so that's for the machine learning. And for the processes, it's also good for you to have sort of processes that adjust for ML fairness problems. We used to call them, we actually do call them human in the loop. So which means sometimes when you have decisions that your model makes and you're not entirely sure, it's always good for you to have processes that can adjust, so you can make a human actually review it before you deploy. And also, it's also good that every decisions that you make, there's this sort of a data-driven analytics pipeline that explains all the decisions. Okay. And then the next is sort of accountability. And so when I talked about fairness, I talked about data and machine learning. But for accountability now, it's actually about processes and decisions, which is, and I just mentioned this, recursing to human escalation process. And then also make sure that you can audit your processes and your decisions, right? So every sort of processes, every decisions that you make, you can actually audit it. And another reason why you also want to do that is because of compliance reasons. So things like the GDPR, the FDA sort of HIPAA compliance, the GXP in healthcare, for example. If you're in finance, there's actually the Consumer Finance Bureau. So they have sort of this compliance where you need to make sure that you can have like a lineage tracking of your machine learning process, but also your process and your decisions, you can actually audit them. So you see that a lot in sort of high-stake decisions, like in finance, healthcare, even in things that has to do with like even government decisions also. And so finally, this last part, which is transparency. And so what transparency does is it brings together machine learning, the processes, and the decisions. And so the first thing about transparency is your model actually interpretable? Can you interpret your model? is your process, is it clear? And can you explain the decisions for customers? So I think one of the sort of, for EU, I think GDPR actually asks that companies that are using EU citizens' data to make decisions, they need to be able to explain it. And so the difference between interpretability and explainability is that when you have a machine learning model that you can actually sort of interpret every decision that it makes, it means that you're talking about interpretability. Now, the other part is that you can have models that are extremely complex, where you have like an increased complexity. And what you can do is that there are techniques called explainable models or explainable techniques that you can apply to it for you to then explain the decisions to the customer. And so for the remainder of this talk, I would actually be talking about model explainability. So which is how, if you have a model, how do you explain the decisions that you get? And so let's take sort of a simple a machine learning problem using the same data sets that I mentioned, and you want to build a linear model to predict the final grade. So you have like the age, the parent education, the gender, and you want to use it to predict the final grade. So what you can do eventually is that your model can come back and say, look at this factor and multiply it by a certain gender, by a certain age, by the education, and you get the final grade. So this is a straightforward linear model that the complexity is actually low, but it's highly interpretable. Because it's highly interpretable is that because these numbers are they're the feature importance. And what happens is that you can, from here, you can just say, oh, actually, maybe the gender and the parent education have the most influence on sort of determining school success, for example. Maybe not, you don't know, but at least you have a model that is straightforward, that you can actually explain the importance of each features in your machine learning model. Now, let us increase the complexity of the model a little bit from a linear model to a non-linear model. And so you want to use it to predict the same thing. And in this case, you have 0.02 plus female multiplied by age multiplied by 0.01 plus age multiplied by education squared. And so now you have a sort of a model in like the non-linear regime, but the complexity is high, right? And so when you look at this, you don't understand what's happening. You look at it and you say, how does age times the square of education even make sense? You know, so you cannot explain. And that's where sort of feature importance comes in. That's where you said, oh, I actually don't, what are the important features here? Do I have to sort of take the age and sort of take like the cube of the age, and then I say, oh, okay, that's important, right? And so that's where explainable machine learning comes in. And so in machine learning, there's something called SHARP, which I would explain some of the background. And what it does is that for each feature that you have, in this case, the feature could be the age, the gender from the data, you get computed importance, so which means you can actually calculate the importance of each feature for you. The next one is that it is model agnostic, so which is any machine learning model that you give it, irrespective of the complexity. So from sort of very simple models, not really simple, tree-based models like XGBoost, to like complex AI neural networks. It is model agnostic, so because what it does is that it computes the importance after you've built the model, so it does that. But also, it gives you local interpretation. And so the idea of local interpretation is that when you develop a model and you're making a decision so I can give you an example. An example that comes to mind is, let's say you have different sets of data to sort of predict, for example, if someone is maybe going to have chronic kidney disease or cancer in the next 90 days. And you have a lot of data. So let's say you have data from the electronic health records and maybe claims data. So you could think of it as you have something like the DX, the diagnosis, the procedures, the PX and the RX, which is actually the sort of recommended medications that the person is using. So you can take all this data, right? And then you can develop a model and say, oh, in the next 90 days, this person is going to go from a CKD stage 3 to 4, for example, right? And so, but what the SHAP does is that the interpretation is not going to be a global interpretation. So it's not going to be an interpretation for all the data you're trying to make inference on. So for each one, you should say, oh, maybe because this person has been on this medication, or there's this certain diagnosis, or there's something different, this is why we think this decision, like the machine learning model actually made the decision. So that's where local interpretation sort of comes in. And for SHAP, if you take a combination of this local interpretation, you actually get the global interpretation. You could think of it as an average of all the sort of shapely values, and that gives you interpretations for each instance. I'm not going to dwell on this slide too much, but in machine learning, there's something we call the accuracy interpretability threshold, which is what are you building for, right? Do you want a high accuracy with a model that is not interpretable, or you just don't care, depending on what you're trying to optimize for? And so this is actually showing some models that as you go, so you have like models that they're very complex, but they give you good predictive performance, but you cannot interpret them and you cannot explain the decisions that they're making. And so I was talking about SHAP, which is this explainable machine learning methods. And so what they do is, so this SHAP is actually taken from shapely values. And what we have done, like what machine learning scientists have done, is that they've actually adopted the concept of shapely values from game theory. And then they deployed it in a machine learning context. And what it does is that it quantifies, so if you have like a player playing a game, it actually quantifies the contribution of each player if you have multiple players to a game. And then also, it actually provides a means for you to distribute payoff generated by a game to the different players based on their contribution. And so I would go ahead and sort of explain the intuition around shapely value and game theory and how it actually applies to machine learning. And so if you look at this image, so P sub I, which could be P1, P2, P3, they're actually game players, right? So they play a game and you have sort of payoff for them, right? And so one intuitive way is for you to sort of assign contribution to the single players, and then you want to see how much payoff they get. So P1 plays a game, I pay P1 $25. P2 plays a game, I pay P2 based on the contribution $100. P3 I pay $150. But actually, that would be problematic. And so the idea around this, intuition around the shapely values is there. If you take P1 and you add P2 to P1, and both of them play the game, right? What is the addition of P2 going to do to P1? And what you can see is that you have, like, in some cases you would have increased payoff. In most cases you have increased payoff, and in some cases you have reduced payoff. And so that's sort of the idea of shapely value justification. And that's how in machine learning, what happens is that you have age, you have gender from the data that I was explaining, and also you have maybe parental education, right? And so what you do is that you actually assign payoff to them based on their individual contribution and also their contribution in relations to the other. And so the sort of justification is, so there are just four justifications, which is that you actually want, if somebody doesn't contribute, they get sort of zero attribution. So the payoff is zero. And then if you want it to be sort of efficient, you want it to be symmetric so that you sort of have equality. If players actually have sort of equal contribution, they should receive equal attribution. And also you want to linearize it. And so that's the sort of idea around shapely values that we use for explaining sort of machine learning models. And in this case, if you have like a game payoff, right, that's your model prediction in machine learning. Your players, each player in this case, from the game theory, are actually your features. So your features are the things that you have, the data that I explained, like the age, the parental education, those are your features. The subset of your players are subsets of your features. So which means on the age, you could have like 10 years, 11 years, depending on what you're looking at. Specific players are specific features. So you have a direct correlation or sort of a one-to-one correlation between this idea of game theory to machine learning. And so this explainer, this sort of sharp algorithm has been, it's really good. What it does is that it solves it for a really good sort of runtime complexity. It's model agnostic, and it sort of calculates the approximation. And so we use Sharp and an open source implementation of Sharp called kernel Sharp to actually explain models. So when you have a complex machine learning model, you can make your predictions, but also you can, in a model agnostic way, explain whatever is happening in your model, how your model is actually making that decision. And that actually brings me to Amazon SageMaker Clarify, which is, so Amazon SageMaker is actually one of AWS cloud services, which you can actually run and do end-to-end machine learning from your sort of orchestrating your data pipeline to deploying your model and monitoring your model in real time. And so, but for SageMaker Clarify, you can actually check bias in your model, and also you can sort of provide explanation for every decision that your model makes. And so Clarify actually explains your machine learning models and assess your data and your models for bias. And some of the things that Clarify could do is that it actually makes it easier for you to identify bias in your data set during data preparation. And so what you do is, if you have attributes, you specify this attribute. It could be gender, it could be age, and then it runs a set of algorithms to detect if you have any presence of bias in those data. And then you can also have like a visual report. So it gives you like a report, and it tells you what are the sources of your bias, what are the measurements, and it will flag if your data is imbalanced. So that's one thing it can do. It can also detect bias in your trained model, and so which means you can actually check your trained model for bias. It can check if it has produced like a negative result more frequently from one group than another. And then you can actually then look at the trained model and then get a visual report that sort of identify the bias that you get for each attribute that you have in your data set. It gives you it actually explains the overall model behavior, which is the global interpretation. So if you have your trained model where you have some model input, it can actually give you like very, very sort of detailed explanation of which features actually contribute the most to your model. And this is always important when you're building machine learning model and you're considering compliance requirements. So in some cases, there's some compliance requirements where you actually want to be able to provide details about sort of the behavior of your overall model, of your overall deployed model. And then you can get individual predictions, which is you can have local interpretation for every single instance that you make or that you predict. So it will give you every sort of individual prediction and actually give you transparency into your model decisions, and that is always very important. And then in some cases, you have models that you're actually deploying over time. And so what it does is it monitors your data and also monitors your model for changes. So if there are changes in the way your model is making predictions, so it actually looks at it. So in machine learning, we call it model drift. So it looks at model drift and also data drift. And you can actually monitor it and alert. So you get an alert if you have like a shift in your input from your data, and it tells you, oh, your model is actually not doing well because we're monitoring it over time, and the data that we have there's some input shifts in it. And so then you can go back and maybe retrain your model, for example, or try to find some other data to work with. And then finally, I'm actually going to talk about integrating Clarifai into MLOps. And I mentioned MLOps is like sort of doing DevOps for machine learning. And so there are actually 5 sort of different stages, which is with sort of the SageMaker ecosystem. You can use Data Wrangler with Clarifai to collect and prepare your data. And so with that, you can actually measure your bias metrics. You can train and tune your model with SageMaker training. And with that, you can sort of tune your hyperparameters. So your hyperparameters are sort of parameters that you use to optimize your model. And so with that, you can actually measure and tune these bias metrics. And also you can measure the explainability metrics that you're looking at. You can evaluate and qualify your model. And all this is sort of across the machine learning lifecycle. So with SageMaker processing, you can measure bias metrics. And also you can measure sort of the other explainability metrics. And then when you sort of deploy your model in production with Westin, you can catalog all the model metrics in real time. So if there are changes, you can see it. And then for SageMaker Model Monitor, that monitors your model over time. So in production, you can actually sort of, you look at the bias metrics, and if there's a drift over time, it actually monitors that. And if there's also a drift in sort of the explainability that you're looking at, it also monitors it over time. And so what happens is you can integrate SageMaker Clarifai across sort of your machine learning lifecycle and use it for MLOps. And so in summary, I think in this talk, I've been able to sort of lay the foundation for bias in machine learning, sort of explain how fairness is important, and as sort of data practitioner, machine learning practitioner, we should sort of keep thinking about what kind of outcomes do we want our machine learning models to produce, right? And then also I'd explain sort of explainability, a machine learning model interpretability with sharp and Shipley values, and then an introduction to SageMaker Clarifai, and how you can use SageMaker Clarifai for your MLOps lifecycle. So thank you. Do we have questions? You're a data engineer? Okay, nice. Okay. Yeah.
One question is, before the data gets to me, are there any standards or recommendations on attribute collection, especially in legacy systems? I'm thinking particularly about the disability case that you did.
Yeah.
If attendance wasn't part of the data model, then the inference that disability plus attendance wouldn't necessarily be there. So are there groups that represent particular interests in providing standards of attribute collection? So disability groups might recommend particular attributes. Are there groups like that? Or are there standards groups that develop recommendations for the systems that collect the data?
Yeah, I actually don't know of any group that does that, but I think it would be really good to have that, to work and sort of collaborate with, for example, the example that you mentioned, disability groups or the disability advocates, for example, and for me, thinking of this under responsible AI, right? That's where you start thinking about sort of inclusiveness in your machine learning or AI process, right? And then you begin to think about how even what predates you developing your machine learning model is actually the step where you're collecting your data, right? So first you want to understand your data. You want to understand if you have systematic errors in your data, but also in some cases, if you have like data that are missing. So in machine learning, what happens is that if you have data that is missing, you could actually do missing data imputation. So you could say, let me impute this data with the average age of the kids, or the median attendance, for example, right? But you shouldn't be doing that if you actually don't know the reason why your data is missing. So you want to know, is it missing at random? Is it just missing not at random? So there are a lot of mechanisms that you can put in place to check that. And I feel that that should be part of data quality check or data quality control, and inclusiveness should be part of that too. Yeah, thanks. Yeah. Are there any other questions? Okay. In the absence of no questions, thank you, everyone.